So remember, we're talking about families of stars, and of course, families are complicated. And this is our second characteristic, which is luminosity, or the amount of power the star has. And you can see that some of those people have a lot of energy, and some of them don't have a lot of energy. And there are methods for classifying the amount of energy that a star in the universe has, and we're going to look into that. You might think, as the ancient Greeks did think, that if a star is bright, it must have a lot of energy. And if a star is dim, then it must not have a lot of energy. And conversely, the Greeks also thought that not only was that related to energy, but that everything was the same distance as well. But you know that just because a star is bright doesn't mean it is close. And just because a star is faint doesn't mean it is far. And we need a measure for the true power of the star, because these two stars in Orion, Betelgeuse and Rigel, both have very similar brightnesses. They're very bright. And you might think that they are both the same distance away, and they are not at all. We measure their relative power by a quantitative measurement called luminosity. So let's take a look at that, because what we see in our eyes is known as an apparent visual brightness. Sometimes you'll hear it as apparent visual magnitude, but it is our perception of how bright the star is and related to a classification. But as you can imagine, there's a lot of subjectivity to that. Luminosity is the power of the star regardless of its distance. Let's look into that a bit more. This luminosity is part of an equation that says that the apparent brightness that we see is proportional to the luminosity measure over the distance squared from Earth. So I wish that square was correctly as an exponent, but the software doesn't allow that to be kept. So that is a exponential distance squared. This relationship of apparent brightness proportional to luminosity over distance squared can be manipulated, obviously, to find apparent brightness, or to find luminosity, or to find distance squared. And we do manipulate this equation. We get into luminosity that is related to apparent visual magnitude. We have to understand apparent visual magnitude a bit better, and this perception. It's a scale that is really tough to abide by. The scale is that the brighter the object is in the sky, the more negative its apparent magnitude. The apparent magnitude is measured as m_v, as in magnitude visual. And look at this. The sun, the very brightest thing in the sky, is like around a -27. The full moon, about a -12.5, -12. Right around 0 is the stars Rigel and Betelgeuse, which are bright for stars, but it would have been a much easier scale if the brightest thing was the most positive and the faintest thing was the most negative. That's not the way this scale works. And that's why I want to get right into luminosity, which is a much better quantitative measure. So let's look into that a little bit more. When we talk about luminosity, we're actually talking about the total emissions of the star, meaning the gamma rays, the ultraviolet rays, the visible wavelengths, the infrared wavelengths, the radio wavelengths. All of the emissions and all of the wavelengths of the star go into the luminosity. And you can make an analogy to remember something that we've talked about before, the inverse square law. The inverse square law is very important in astronomy because it seems to discuss wave behavior, and we relate it to gravity. That's what we've talked and used this graphic for before. Now we're looking at the behavior of light and waves in light and the inverse square law, and relating luminosity and the total emissions from a star and the total light that it puts out, and the behavior as the apparent brightness that we see. So let's discuss a bit. If gravity or light was a can of spray paint, that means that the farther that spray paint needs to travel, the less is going to stick on a certain small area right here. So for instance, this area right here is the same as this area. It's this just much, much farther away. This area is going to get a lot of paint on it. This area is going to get very little paint on it. This area is going to get a lot of light on it from the star. This area is going to have very little light on it and a very low apparent brightness. We can actually quantify that over distance. That's what the inverse square law tells us for gravity. A source of gravity will be very strong, close, and it will be less strong and less strong and less strong as the distance gets greater. Same thing with light intensity. Let's look for it a bit more. When we look at a star here, and we look at its impact on Earth here through 1 astronomical unit. Actually, this would be our Earth right here at 1 astronomical unit, at 2 astronomical units, at 3 astronomical units. So that would be at about a little bit farther than Mars, okay? So when that star shines on, and I'll change this to Mars, it gets far less light than what we get right here at the same amount of area, but we're just farther away. So when we have 2 measures of this equation, when we have our perception of how bright that star is from our distance away in the sky, and remember, this is a really subjective measure, but there are ways of making it a bit more quantitative. Not great ways to make it a bit more quantitative, but there are ways. If we have this measure and we have a catalog of all these apparent brightnesses, and if we have the distance from the star to the Earth, then we can calculate for the total emissions, because we have 2 out of 3, and we can solve for the third. And in fact, if we look at this, we can look at the same luminosity close by, and then less light getting here and less light getting here and very little light getting out here. But you can look at this same equation and we can look at light we can find apparent brightness when we have 1 watt of luminosity and 4 meters distance. Let's pretend this is 1 watt right here, and 4 meters. There's 1 meter, 2 meters, 3 meters, 4 meters. How much apparent brightness is going to fall on one of those blocks? It's actually going to be 1 watt per 16 meters squared. Okay, does that make sense? 4 meters away, a square, 16 meters square, you're not going to get 1 watt per meter squared as you do here. You're going to get 1 watt per 16 meters squared for your apparent brightness that I perceive for that light source that's quite a ways away. Now, I usually have that in a catalog, or I can see it and make a measure on my own eye of the apparent brightness. So I'm usually not looking for apparent brightness in this equation, but I can look for luminosity from this equation. And if I have the apparent brightness, which I can either see or look up in a catalog, and if I have the distance at 4 meters, here's my star, and here's my 4-meter distance, and I have the apparent brightness at 1/16th meter squared at 4 meters, then I can solve for luminosity. So in other words, I can move the distance squared over to this side of the equation. Apparent brightness times distance squared is proportional to luminosity. I can get this, and guess what? 1/16 meters squared times 16 meters squared equals 1 watt of luminosity. All right, so I found my luminosity there. And I could also go and find distance, which is basically what we use this equation really for. But I wanted to show you all the different ways to use the equation, because when we were looking at radar reflection and when we were looking at parallax, we were coming up with problems. So you should know that knowing this luminosity, especially when we can measure it with satellites that are above the Earth's atmosphere, we can measure it with more precision, and we can tell a distance from luminosity. This is another technique that you use with your family snapshot for this crazy family that we were talking about. We need another technique to look at luminosity. So let's find distance from this equation. Well, to find distance from this equation, I'm going to multiply everything times distance squared, so I can cancel this out and move it over here. And I get distance moved back over here. So I've got distance squared equals luminosity over the square root of apparent brightness. And then I take a square root of everything so that I get distance alone. Distance alone equals the square root of luminosity over the square root of apparent brightness. If you don't know how to figure that out, spend some time working on this slide. But then I fit in my, after I've got this, I fit in my known quantities. I've got my 1 watt of luminosity that I'll take the square root of, and I've got my apparent brightness, which is 1 watt over 16 meters squared, and I can take the square root of it. But you know what? I don't even need to do that, because I can flip this around. I can put 16 meters squared over over the square root of 1 watt, cancel out my square roots of 1 watt, and then I've got the square root of 16 meters squared equals 4 meters. That is my distance. And this is an important way to look at distance when you can't do parallax. You can send a satellite up. The satellite can take a very good view and get a good luminosity measurement. And you already have a catalog of the apparent brightness. Then you can figure out the distance from there. This is exactly what a satellite called Gaia does. The GAIA stands for the Global Astrometric Interferometer for Astrophysics. It's put out by the European Space Association, Space Union, and it also stands for the Greek symbol for the Mother Earth, Gaia. But it has a mission to make a 3D model of the universe. So it's the perfect thing to look at for our family snapshot. They do distances from there, and they also do apparent brightnesses for stars that we cannot see with our eye. So they are doing approximately, I think they're up to 10 billion stars now, and it will take about a decade just to analyze all the data. They are working with 2 variables, and they're solving for luminosity and sending all that data back. It's the exact same triangulation that you were working with. Now I'm going to introduce our family snapshot here of stars. Our family snapshot, all our data goes into a graph, so that this graph starts out with luminosity here, and our luminosity measure is 1 for our sun and the power that our sun puts out. Obviously, Rigel, a very bright star but very far away, is over 10,000 times more powerful than our star. So this is a type of data measurement where we measure luminosity on the y-axis. And we will have more about this soon.